Okay, welcome to Geometry Project, geez, what am I on, 15? Welcome to Geometry Project 15. This is Ptolemy's theorem, and it's a very clever application of the stuff we've been talking about with the Simpson line. So, but before we get into the statement of the theorem, we just have to go back to section 1.9 for a second and recall a separate thing we proved about pedal triangles. So, ABC is any triangle, and we pick a point P, and we draw perpendiculars to the sides. And we showed the sides of the triangle, B1, C1 equals A, side length A here, times AP, the distance from A to the pedal point, over 2R, the radius of the circumscribed circle. Similarly, the other side, C1A1, was equal to the length of the opposite side B times the distance to the pedal point, BP, over 2 times the radius of the circumscribed circle. And for the third side, A1B1 is C times the distance from C to the pedal point, over 2R. So this is going to come in handy in just a second. I just wanted to remind you of that. So let me draw another picture real quick. On what we just talked about with the length of the sides of the triangle. Now you say, there is no triangle A1B1C1 here. Well, yes there is. It's right here, A1, B1, C1. The fact that they're all in a straight line on the Simpson line is just a degenerate triangle, but the formulas still hold. The distance B1 to C1 is equal to side length A times AP over 2 times the radius of the circumscribed circle. A1, C1 is B times BP over 2 times the radius of the circumscribed circle. And A1, B1 is C times CP, the distance from C to P over 2 times the radius of the circumscribed circle. Although, in this case, we actually have a very interesting situation in that C1B1 plus B1A1 happens to equal C1A1. Looks like I wrote it backwards, but you know what I mean. But B1C1 is A times AP over 2R. Plus B1A1 is C times CP over 2R equals A1C1, which is B times BP over 2R. Now, everything's divided by twice the radius of the circumscribed circle, so we'll just delete that. Just multiply that all out. We have an interesting little formula. And sorry for I just want to check that this formula, this interesting little formula is in view of the camera. Yep, it is. Okay, so what does this mean? So let me draw in green AP, CP, and BP. And let's what color would be good here? How about purple? A times AP plus C times CP equals B, set here, times BP. So what do you see? I have a quadrilateral inscribed in a circle. I have quadrilateral APCB, and what I've said is the product A times AP is one set of opposite sides. Here's AP and here's side length A of the original triangle. C times CP, where's side C? C times CP is a side of the triangle, one side of the quadrilateral. C, CP times the other side, sorry, I erased the plus, equals B times BP, B times BP, that's the diagonals. And so we've stumbled upon, just completely by accident, a very easy theorem that says the following. For a cyclic quadrilateral, in other words, a quadrilateral inscribed in a circle, the sum of the products of the pairs of opposite sides, A times AP, C times CP, in other words, here and here, here and here. The sum of the product of the pairs of opposite sides is equal to the pair of the diagonals. And that's called Ptolemy's theorem. And so this is just a very interesting application of the Simpsons line. You do a lot of work to prove that you get a line there, and you do a lot of work to prove these formulas for the distance of the sides of the pedal triangle. But when you do all that work, you're rewarded with a very easy theorem about cyclic quadrilaterals. Very unexpected. Very nice surprise. The book proves a second theorem that follows from the triangle inequality. I think I'm just going to skip it. You can see it in the book, and but I just think this result is really nice and a great example of how these little treasures in geometry can just sort of come right at you. Couple of neat little problems in this section, especially problem number 3. So if you want to spend a little bit of time in section 2.6 of Geometry Revisited, you're going to find some neat problems. You can find a neat theorem. One theorem I decided I didn't want to talk about, only because I think the first theorem is this proof of Ptolemy's theorem is so great. Anyway, that's all for today. Thanks for watching. A few more interesting results about the Simpson line tomorrow.